Ladies and gentlemen, I am Alberto Montanari. I am the incoming Vice President of EGU. This is my first formal speech, so I hope that you allow me to be a little bit, let's say, nervous for this. And I am pleased to welcome you to the lecture, the medal lecture of the Alexander von Humboldt Medal of the European Geosciences Union. The Alexander von Humboldt Medal recognizes the excellent contribution by researchers who worked for and in developing countries. It's a medal that was established many years ago at the beginning of the history of EGU to recognize the relevant efforts that many of the geoscientists make for promoting developing countries. It's my great pleasure today to introduce the recipient of the 2018 Alexander von Humboldt Medal, who is Filippo Giorgi. It's a great pleasure for me because Filippo, I think it's a real role model for scientists that aim to contribute to the development of developing countries. And Filippo, I think it is a relevant example for what he did for capacity building. I think it's better if I introduce him by first reading the citation. The 2018 Alexander von Humboldt Medal is awarded to Filippo Giorgi for outstanding research on modeling regional climate change, focusing on developing countries, including effective outreach in terms of joint education programs and institution building. One could say many things about Filippo. One could enumerate the contribution, the excellent contributions and the citations that Filippo received. I would like to emphasize that he has established the Global Regional Climate Research Network. You may think that global and regional are antithetic terms. Filippo proved that they are not. He was able to focus on global climate change and regional implications. And with this network, he promoted capacity building through workshops, through education programs, always with special attention and focus on developing countries. For this reason, I think that his contribution is unique. It's a unique combination of academic excellence and a sharp awareness of local needs in developing countries facing an uncertain future. For this reason, I think that he is an excellent and deserving recipient for the EGU Alexander von Humboldt Medal. Today we are listening to the medal lecture given by Filippo. The actual award was given yesterday during the EGU award ceremony. So today we are not actually giving the medal to Filippo because it was already given. Today we are listening to a review of his experience and contributions. Now we have to take a picture with Filippo, so I hope that you allow us a couple of minutes and then Filippo will be invited to deliver the medal lecture. Thank you very much for being here, and I really appreciate your numerous attendance today. Thanks.
Okay, so the difficult part is over. The picture part is always not easy. So, of course, I thank very much the EGU for this award. Already yesterday I said how proud I am of being recipient of this award. In my lecture today, actually, I will talk about something that I've been interested in more recently. I will not talk about regional modeling, which is probably what most people expected, but I will talk about the response of the hydrologic cycle to global warming. Before I do that, let me thank a few people. First of all, Thomas Alenka, who's sitting here in the front. He's the guy who actually nominated me, and of course all the people that wrote supporting letters. I want to thank all the people who worked with me in my career. I've had 2 professional careers. The first one was at NCAR, where I worked between 1984 and 98, and I have to say these were really wonderful years. NCAR is a great place for young scientists. And then in 1998, I moved to ICTP, the International Center for Theoretical Physics, and of course, I want to thank all my collaborators, postdocs, students, and so on. Let me say that these are 2 of the most beautiful places where you could actually work, so I feel very, very lucky for this. And of course, I want to thank my family for supporting me and putting up with me, which has not been always very easy. Let me say a few words about Alexander von Humboldt, because as I said yesterday, after I learned that I received this award, I actually want to learn more about him, so I got this book called The Invention of Nature by Andrea Wolf. It's a wonderful book that talks about all the contributions and the life of von Humboldt. Really think you should read it. And I realized that he was really, as I said yesterday, a rock star of science of the 18th and 19th century. He was one of the most prominent scientists, and according to the book, he was, after Napoleon, he was the most famous person in Europe. He made some fundamental contributions to many areas of the natural sciences, but the most important thing, I think, is that he was the first scientist to really view the Earth as an interacting system. In some ways, he's a precursor of modern Earth system science. He was also a very adventurous person. He traveled around the world. He was an explorer. Took first-hand observations, which is very different from what I do, because me and tools don't get along very well, so I never take observations. I live in a model world. But very importantly, he was very keen on learning from local know-how, which is something that we also try to do. So let me say a few things about what we do in ICTP. As Alberto said, our activities is mostly modeling, and it's mostly modeling aimed at fostering science in developing countries. So we develop tools that can be used. They don't need super-duper machines or large infrastructure. Of course, the main tool we have is the one that I've been working on for the last 30 years, the regional climate model called RegCM. But we also have a tropical band model. We have an intermediate complexity model called SPEEDY. We have many impact models. The thing about this is that these are open source, public codes. We provide workshops. We teach people how to use them, and also how to install them on their infrastructure. This is the network that Alberto's mentioned. We are very, very proud of this. It's a network of scientists from all over the world, literally. There are about 800 participants, at least 800 people on the email list for this network. And we do all sorts of things, workshops, a visitor program, projects, and so on. So if you are actually interested in joining us, send us an email, not to me, because I'm getting too old to read too many emails, but you can send it to our staff. I also want to say a couple of things about the Cortex Project. This is an international project in which for the first time the regional modeling community got together to produce a new series of projections worldwide. You see the Cortex domains there, and we are at the second phase of this project, and over the next year there will be a huge set of new projections, a lot of data that will be available, and by the next year session, EGU session, I think we'll have many papers on this new activity. So let's go to the actual topic of my talk. I have a little bit of a cough, so please, if I start coughing, bear with me. This is the basic question that I want to address. How will global warming affect the Earth's hydroclimate? Hydroclimate, I mean essentially precipitation. How will precipitation change in the future? So let's look at the hydrologic cycle. This is a picture from a paper by Kevin Trembert. It shows the hydrologic cycle. You know, the engine of the hydrologic cycle is the sun. It heats the surface, and then the surface evaporates. You have ocean evaporation. You see here the fluxes are these slanted numbers. These are the units. You see that about 85% of evaporation is from the ocean and about 15% from land. This water gets into the atmosphere, eventually travels around, it gets into clouds and rain system, and it rains back down. And you see here the actual precipitation fluxes over ocean and land. You see most of it actually rains back over ocean. The atmospheric lifetime of water vapor is order of several days, 5 days, a week, or something like this. And this means that if you look at climatic timescales, you have a balance between evaporation and precipitation. Essentially, whatever water gets into the atmosphere eventually comes back. In fact, if you add these numbers, the precipitation and evaporation numbers, you'll see that they actually balance out. However, evaporation and precipitation are two very, very different processes. Evaporation is a slow process that happens all the time. There's always evaporation from the oceans, about 2.8 millimeters per day. And there's not a great spatial variability. Of course, there is some spatial variability, but not really a great spatial variability. Precipitation is totally different. It's a very local process. It's a highly intermittent process. Essentially, if you have a precipitation system, it draws rain locally from a radius of about 3 to 5 times the radius of the system itself. So a synoptic system will draw moisture from a few thousand kilometers, but a convection system from a few kilometers. In fact, if you actually look at data, you will see that about only 25% of the days are rainy days. And since it doesn't rain all the time, actually it rains 5 to 10% of the time. So it doesn't really rain very often. This means that when we look at precipitation, we could look at things like this, which like mean precipitation, but this is really not very meaningful, I think, because you can get 10 millimeters per day rain in one event or in 100 events, and this has very different implications. It is much more useful to look at things like this. So precipitation intensity distributions, like these ones here, or some indices of precipitation, for example, in this case, the 95th percentile. So we can actually reformulate our basic question, asking ourselves, how will the characteristics of rain change with global warming? We don't care very much about mean precipitation. This is really not very important information. Of course, it is some good information, but what we really want to know is how will the character of precipitation change? And more research is going into this direction. This is just for some nomenclature. I will talk about both CMIP3 and CMIP5 models and run. CMIP3 are the projections for the 4th IPCC report. You will hear things like the B1 and B2 scenarios are low-end scenarios in the CMIP3 dataset, or A2 is a high-end scenario. For CMIP5, you will hear the RCP 2.6, which is essentially the Paris Agreement scenario, 2 degrees compared to pre-industrial temperatures, and the high-end scenario, RCP 8.5. RCP 8.5 and A2 are roughly similar to each other. Okay, so what happens at the global scale? The global scale, you increase the temperature of the oceans, you increase evaporation, so you expect an increase in global precipitation. This is essentially what all the models project. These are some examples of models from the AR4. There is a spread, some uncertainty. This uncertainty is actually not related to precipitation, but it's actually related to evaporation, because evaporation determines what eventually globally will come back down. But all the models project an increase in precipitation. This information is kind of useful, but I would say not so much. You could look at geographical distribution of precipitation. This is the so-called rich get richer, poor get poorer pattern of change. This has actually survived several generations of model projections. Ever since I looked at global models, the changes always kind of look like this. You have an increase in precipitation in the equatorial regions, especially ocean regions, which is a response to increased evaporation, so increased convection. You have an increase at high latitudes because of the poleward shift of the storm tracks due to the greater warming in the tropical troposphere and the expansion of the Hadley cell. And then you have drying in subtropical areas, including, of course, the Mediterranean, which is one of the hotspots that we identified in a paper of 12 years ago now. This is the AR5. You will see it's very similar to the AR6. But the real question is, how richer will the rich get? If all this extra water comes in big floods, are they really getting richer? Maybe not. And how poorer will the poor get? So to assess those questions, you actually have to look at some other statistics. People have looked at precipitation intensity and the frequency of precipitation, but we'll come back to this. The first thing you can do is to look at how the PDFs of precipitation change. So this is an example, of change in precipitation intensity distributions in the Max Planck model for 4 time slices here. It's RCP 8.5, so a high-end scenario. The blue slice is a reference period, 1980 to 2010, and then you have 3 future time slices, 2011, 2040, 2041, 2070, and 2071, 2100. You can think of 3 different levels of warming. It's about 4 degrees for the last time slice, 2 and something for the middle one, about 1 degree for the first one. Now, these are the PDFs, but a better way to look at this is to take, this is a logarithmic scale. So if you take differences between PDFs, you're not going to see much. But if you take ratios, you're actually going to see how things change in the future. So this is the ratio, bin by bin, of future PDF and reference PDF, okay? The value for each bin. This is a far future, middle, and near future. So what you see here, you see that for high intensity events, the model tends to produce more events, more frequencies, higher frequency of events. In particular, these events here are the most interesting one because they're all the way up there, not because it's a factor of 10 in the ratio, but because these are all cases in which there are no events in that bin in the present day. So these are unprecedented events. So in the future, at least in the last time slice, we actually enter somehow, you could think of this entering a different, a new sort of climate regime, or at least hydroclimate regime with unprecedented events. In this part of the spectrum, you see a blow up here. You see that you have a decrease in low intensity events. You have an increase in zero intensity events, so you have a decrease in the frequency of precipitation events. And then you have this, of course, increase in the mid to high precipitation events. And there is this threshold where you go from less than 1, so less events, to more than 1. And the very interesting thing is that this threshold doesn't depend on the temperature change. And to be honest, I haven't been able to understand why. This is something that's being found also by other people, why this threshold should be the same for 3 levels of warming, the threshold changes in different regions. Tropical regions is moved a little bit to the right, extratropical a little bit to the left, but you always find this result. And if you don't believe me, you can look at another model. This is the HydGem model. Similar type of things, unprecedented climate, and here. So you have this decrease of low intensity event, increase in high intensity event, and this sort of threshold that gives you this change in the regime. We also looked at regional model, high resolution MedCortex simulation. This is our simulation. We have shown in this paper that actually reproduced quite well the observed PDFs, at least over the Alpine region. And also in the regional model, you find essentially the same. This is for the whole Mediterranean region. Maybe not exactly as precise of a threshold. There's a little bit of a spread there, but something kind of similar. You can actually look at the Alps. It's moved to the left a little bit, but again, you find the same result. So this seems to be quite a robust response, at least of the models. Global models, regional models, low resolution, mid resolution, high resolution. These are 10 kilometer data. So, given that the PDF changes in this way, in a couple of papers, 2011 and 2014, we try to address this issue of how the regime of precipitation will change with global warming by looking at a number of different indices, but interconnected indices. Okay, so we looked in particular 6 indices. We started with 2 in 2011, then we added 4 in 2014. You see here some are standard indices. SDII is the mean intensity, R95, this is the fraction precipitation about the 95th percentile, mean dry spell length, mean wet spell length. These are sort of standard indices. But we also looked at something that we call the precipitation area, which is the spatial counterpart of the frequency. So if you expect precipitation to have a lower frequency, if you take a satellite picture and make an average of satellite pictures, you should be able to see that the area where it's raining is actually shrinking. And then we introduced this high index. If you read the paper from 2011, it means hydroclimatic intensity index, where we actually multiply this index and this one by assuming that the changes are kind of correlated, but okay, this is a long discussion. We looked at 10 GCMs, and also we looked at some observation data set, a global data set and 4 regional data sets. So this is what you find. In terms of the R95, blue means increase. This is the trend from 2005 to 2011, RCP 8.5 is blue everywhere. Mean precipitation may increase, decrease, do whatever it wants. The R95, the extreme precipitation, at least in these 10 models, will increase. SDII, increase everywhere except some desert areas where it doesn't rain anyways. This high int also an increase everywhere. Precipitation area, if the frequency goes down, also the precipitation area you expect to go down. It's red, so it's a decrease almost everywhere, except for these regions where you have big increases in rain. Wet spell length, similar. You have, well, not similar. You have a decrease in the wet spell length, and you have an increase almost everywhere in dry spell length, except for this region. Okay, this we can understand because you have a big increase in precipitation at high latitudes. This is a strange region that for some reason, these 10 models, the dry spell length actually does not increase, but it actually decreases. So if you put all this together, this is the picture that you find. You have, let's say that these are colder or present day precipitation events. So you have a series of like 1, 2, 3, 4, 5, 6, 7 events, and the sides of the box gives you the magnitude of the event. In a warmer climate, you have fewer events, okay? You don't have 7, but you have 4. You have, on average, more intense events, and also more extreme events, and also more concentrated events. So to put all this picture in words, the change in hydroclimatic regime coming out of this analysis is that global warming brings fewer, more intense extremes, and more concentrated events. Now, we try to understand why this is happening, because it's not actually obvious that the number of precipitation events should decrease. It's kind of obvious that the intensity should increase because because of Clausius-Clapeyron, you have more water vapor. But why should the frequency decrease? Why should the events be more concentrated? So we looked at one model, our old friend Max Planck model. And what you see here, if you look at these numbers here, okay? Now the unit here is the percent change of that variable per degree of global warming, okay? PRW is precipitable water, and you see that there is an increase of 8.74% per degree of global warming. Clausius-Clapeyron is about 7-point-something%, but here we use as temperature the surface temperature. And in this model, the tropical troposphere actually warms more than the surface. So this is essentially Clausius-Clapeyron, okay? So 8.74% increase. The intensity, the mean intensity of events increased by 4.58. This is less than Clausius-Clapeyron because it has been shown that Clausius-Clapeyron actually holds for the most extreme events. But in terms of intensity, okay, maybe there are processes going on, is less but not far from Clausius-Clapeyron. And why Clausius-Clapeyron? Because precipitation is a local process, so it depends on the local saturation value, okay? Evaporation, on the other hand, it's a much slower process and much less efficient. It's only 2% per degree of global warming. If you actually look at the CIMI 5 models, this number varies from 1 to 2%, because evaporation depends on many things, on the winds, on the roughness, on many things, okay? Precipitation, sure enough, 2.16. So actually this model has a very good hydrologic cycle. Everything balances out. Now, of course, if this one increased by if the intensity increased by 4.58 and the mean precipitation increased by 2.16, to balance this, you must have a decrease in the frequency. So in fact, you have a decrease in the dry spell length. So essentially what is happening is that this response is due to the fact that precipitation is a local process that draws from the local saturation, and evaporation is a broad process. Another issue could be with tropical convection. There have been papers that have shown that as you increase the temperature of the oceans, tropical systems tend to kind of self-organize into bigger and more localized systems. So this is probably something that is also going on. There are a few papers, I think there was a session here that dealt with this. So I think this is actually very interesting research going on. We actually looked at observations. This is a bit difficult to read. You can actually read the paper, but to summarize the message, if you look at trends between the mid-70s to the mid-2000s, which are the data we have, both the global data set we had and all the regional data sets gave us results that were at least qualitatively consistent with what we have seen. So at least from the models, we think this response is fairly robust. Now, one of the consequences of this response is an increase in extreme events, possibly catastrophic events. You see here data from the Munich Reinsurance Company showing that the number of catastrophic meteorological events is increasing, number of unprecedented events. So we wanted, in a very recent paper that has been just accepted and should come out hopefully the next week or so, in this NPJ Climate and Atmospheric Science journal, we asked ourselves this question, whether we could devise an intuitive, simple, very intuitive metric to quantify how stress is associated with the increase in extreme events, both wet and dry events. Because of course you have increase in wet events because the intensity increases, but also you expect an increase in dry events because you have longer dry periods, okay? Of course you can define drought in many different ways, but in general, you expect an increase in drought. So I like indices, so there we go with another one. We define this cumulative, okay, this, I hope I can explain it well. I have a bit of time to do that. So we defined a cumulative hydroclimatic stress index. The first word is cumulative, so we accumulate now whatever I'm going to describe over time. So we don't miss any event, okay? Because the stress should be something that accumulates over all the events that happen. And in fact, if you have a sequence of events, this can be more dangerous than having one big event. This is a potential stress, and it's defined like this. We first define this variable here. We take a reference period, for us is 1981 to 2010, and we calculate a threshold. This is for wet events, and the threshold is the 99.9 percentile of the distribution for the reference period. So we are looking at really extreme events. We include also zeros, so we're looking at the top 12 events, essentially. So the 12th highest event for us is the threshold for a dangerous event. We actually checked this with European floods, and for European floods, this is definitely a good definition. Then we add up cumulative, remember, all the precipitation above this threshold, assuming that the stress is proportional to how much you exceed this threshold. You say, this threshold is my danger threshold. If I exceed it, I have a higher hydroclimatic stress, hydrostress, let's say. If I double it, I have a very large. If I have only 10% higher, I don't have a very large stress, okay? And then we divide it by 30, because we have 30 years. So we have the stress per year in the reference period. Then we start with the future. Our future starts at 2011. And we have the same threshold as the present day, because that's our danger threshold. And then every time we exceed that threshold, we add that precipitation. Now, if we divide this by this quantity that we calculated, we actually can express this index in something that is a equivalent reference stress years. Okay, so if I get to 1, okay, if this number is 1, it means that I've added 1 year of stress, where this is the mean stress in the reference period. I hope this is clear to everyone. So if climate doesn't change, and I keep adding, after 10 years, this index will be 10. After 20 years, will be 20. After 30 years, will be 30, and so on. If climate actually changes and I get more extreme events, after 10 years, maybe I'll have 12. After 20 years, I'll have 25. So I've added 2 equivalent stress years. Okay, I have added 5 equivalent stress years. If I take out that present climate, then what I can find out is how many equivalent stress years climate change is actually adding because of extreme wet events. You can do the same thing with extreme dry events, where we actually define the dry event as at least 3 months with a precipitation deficit of 25% compared to the reference mean for that month. So if you have a streak of 3, 4, 5, 6 months where you have a more than 25% precipitation deficit, we define that as a drought, quote unquote, or at least dry stress. And they tell me 25% for 3 months is a big drought. And then we add up these deficiencies, the same way that we were adding up the amount of extra precipitation. Believe me, you can do this. Maybe it's not entirely clear, but I hope it is at least the concept. And this is what you find. For RCP 8.5 and RCP 2.6 at the end of the 21st century, okay? After I've taken out 90, which is the number of years if climate doesn't change. So this is the hydroclimatic stress due to extremes, wet and dry extremes, associated with climate change. So if you actually look at the R99.9, you see that you get to values. First of all, you see that everywhere is positive. So extremes increase everywhere. and their cumulative stress is positive everywhere because of climate change. Again, I'm taking out the basic climate. If you look at, if you look at this, you see that you get to values of 200, 150, 200. It means that by the end of the century, after 90 years, you have added 200 years of equivalent stress associated with extremes. To me, this is a very large number. This is for droughts. For what we call droughts, okay? For drought, you have the blue is negative because, of course, there's a big increase in precipitation here. But in many regions, you have an increase up to 100 years, stress years, due to droughts over these regions. For example, the Amazon basin, Western Africa, talking about developing countries. The Mediterranean, of course, it's a very big, dry hotspot. You are adding, I mean, if you're an insurance company, you think that you're paying a certain amount of dollars or euros per year, here you have to add 100 years of expenses to your normal today's expenses. This is the same thing in different continents. So you see that on the average, the RCPR 95 adds 120 years stress. You see the different regions. And also, of course, you see that in 2.6 you have a big reduction of this number. But we put the two things together to calculate what is the total stress due to wet and dry events. So we start with 2020, and we have here 5 thresholds. We kind of thought of this as danger thresholds. So this is yellow alert, orange alert, red alert, purple alert, black alert. Big stress. So and this is additional, okay? This is additional stress years. I've taken out the baseline. So what you see here, you start after 10 years. We start in 2010. We have some yellow alert in some areas, 2030, 40, 50. You start getting some orange alerts, especially. You've seen the hotspots in this case are South America and Africa. Some red alerts start to appear. We are at 270. We have orange alert almost, more than 50% of land. 2080, 2090, 2100. Some areas, they have the black alert. Some areas are adding 300 years. So it's a factor of 3 more years due to this type of stress, due to these two extremes. Now, you can also extend this index by adding some socioeconomic information. Let's say that you have an event. You can associate to this event the damage or exposure. So we did a very simple exercise. We associated to every event a measure of exposure. What does it mean? That if there is a flood in the desert where nobody lives, nobody cares. Or maybe, I don't know, some animals cares or whatever, but maybe the earth cares, but humans don't care. So we actually multiplied this cumulative index by the population in the future, normalized by the population in a reference period. And there are some population scenarios that are associated with the RCP 8.5 and 2.5. So by doing this, you have a population-weighted climatic stress. And since the population is every 10 years, you see how this goes, but I'll show you the animation again. Now, this is when you include population, okay, as a measure of exposure. 2020, you have yellow stress, yellow alert. 2030, you already start getting some orange alerts, especially Africa. Why is orange now? Because we expect Africa to increase its population. So between the increase in extreme events and the increase in population, the stress becomes much greater. Orange alert, look at Africa, boom. 2050, you have red alert almost everywhere. 2060, a couple of interesting things. China went back to yellow. Why? Because in China, at least these scenarios project a decrease in population after 2050. So in principle, yes, the extremes increase, but the actual stress for people is less. Well, there's fewer people affected. But look at Africa. Africa is already at the purple alert level. 2060, 2070 is already black level, black alert. Look at the black over Europe, over the US, Australia, many areas of the world, because in these areas there is also an expectation of an increase in population. So I'm doing very well with time. So this is all summarized in the last figure of our paper, where you have the two scenarios, RCP 2.6, RCP 8.5, average over all the regions. This is without population, so climate only, and with population included. And you see that when you include the population, you have some big spots. These spots means more than, 450, 500 additional stress years. These are huge numbers. I really did not expect to find these types of numbers. But even just with climate, you have a lot of the red spots and some of the purple spots, for example, here in South America. So the conclusions are that the first conclusion is that a regime shift towards more intense and extreme, shorter, less frequent, and less widespread events is definitely a very robust signal in the models. Remember, I live in a model world. So to me, this is sort of reality. Now, I mentioned observation, and I know, Alberto, we had discussions about this, about these trends in extremes and so on, but at least if you look at from 1970 to the mid-2000s, read the papers, you will see that the trends we are seeing in these indices are consistent with this. Okay, so I don't want to say with this that the observations are confirming this shift, because otherwise Alberto gets very upset at me, but definitely at least it's in the right direction. The other thing is that we found in this later paper is that under the high-end scenario, RCP 8.5 is a high-end, but it's not an incredible scenario. Many people call it a business-as-usual scenario. We are still on a trajectory, an RCP 8.5 trajectory, okay? I think the results, it's a very simple exercise. There are big assumptions. You have to bear with these assumptions, and it can be refined in many ways, but I think it shows that you have that the effect of the increase in extremes is really very, very large. And I think it can pose some severe stress on the sustainable development, especially South America, Africa, and some developing countries. The other thing is that under the RCP 2.6 scenario, everything is cut down a lot. Now, RCP 2.6 is Paris, so I'm not supposed to give policy recommendations, but I think this really calls for trying to meet the Paris Agreement. Now, the talk is not over, because I wanted to end with another thing that Alexander von Humboldt did. Again, if you read this wonderful book. He was one of the first scientists to actually recognize the impact of human activity on the environment. Of course, he was looking at deforestation. He was not looking at climate change in a global sense. But he realized, if you read the books, you have some sentences where he realized that humans can really affect our environment. So in some ways, he was the first already in 18th and 19th century to recognize the beginning of the Anthropocene. And so I've done this simple exercise to kind of wonder what he would feel if he was here today. Not to listen to me, but to listen to the IPCC report or something. So this is von Humboldt's view of the Earth system, okay? Everything interconnected, atmosphere, hydrosphere, anthroposphere, biosphere, and so on. This is the Holocene. These are temperatures in the Holocene. This is a paper from Marcotte et al. You know, probably many of you know better than me that the temperature of the Holocene was a fairly stable climate for thousands of years, and many people think that this is the reason that allowed the civilization to grow. If we can call what we have civilization, this is the main reason that allowed us to grow our civilization. So this is until 150 years ago. This is where we are today, okay? This is the warming in the last 150 years. Already by looking at this figure, I think Alexander von Humboldt would think that something very unusual is happening. And then this is the Paris target. This is almost an unreachable target. I mean, to reach the Paris, the 2-degree global warming target, really all nations would have to start putting in a big effort already as we speak. And look already, the Paris target, how far is it from the temperatures, the normal temperatures of the Holocene? This is the RCP 4.5. This is the mid-level scenario that many people think is probably the most probable, but look already how far is it from the Holocene temperatures. And this is the RCP 8.5. So we risk in the next 100, 150 years to give the Earth a perturbation that I don't think it has seen at least for the last 3 million years, maybe during the dinosaur times or something. But the climate was good for dinosaurs. I'm not sure it would be very good for us. So I think that von Humboldt would be very concerned, very interested for sure, but very concerned about what's happening to the, what we risk of doing to our planet today. And I'd like to finish my talk with this slide. There is another amazing individual, actually, who cared a lot about the environment. His name is Hundertwasser. He's actually Austrian. There's a wonderful museum not far from here. I think everybody should see this museum because it's really a wonderful museum. And Hundertwasser was an artist and an architect, but he also was a big environmentalist. And he was very worried about what we are doing to the environment. So in many ways, I think von Humboldt and Hundertwasser would have liked each other a lot and were joined in expressing our concern that what we are doing to this planet, if the planet goes up by 4 or 5 degrees, like RCP 8.5 says, it's really unclear to me. We tend to say 4 degrees, okay, more events or whatever, but how this interconnected system can respond to this is really very difficult to understand. So I think I want to leave you with this message, it's my own message. Since I'm here as a medalist, I can say it at least for once, that my message is I think we should try to do whatever we can not to get to this point, because we don't know what we will risk if we actually get there. And with these words of wisdom, 50 seconds ahead of schedule, I thank you for your attention. Thank you very much.
Thank you, Filippo, for this very exciting talk, and also thank you for mentioning the discussions that we had that were really exciting. I personally would have several questions to ask you, but I prefer to give the word to the audience. I hope that you have my same curiosity and you have questions for the speaker. Please, if you can, please reach the microphone. It's behind you, and if you can, please introduce yourself.
Yes. My name is Angelo Rubino from Venice in Italy, and I have a question. So in the realm of the models, you say that there is more or less a consistency between the observed trends and the so simulated values. But how technically you can explain this, given the fact that the models in general don't have the resolution of that phenomena, and even so the clouds physics seems to be so not trivial to be treated in the model? Thank you.
Okay, well, first of all, some of these responses are basic responses related, for example, to Clausius-Clapeyron response and so on. This response also happens in very high resolution models. I showed you some response from regional models that go to 10 kilometers. If you actually look at one of our papers, it's the same type of response you even find with convection permitting models. So this response of less frequent and more intense events in the models, you are right, they have a lot of limitations in representing convective systems. But in the model, in the range of models with many different resolutions seems to be very, very robust. So given the limitations of the models, but given that there is such a range of models that give a consistent response, I find it at least, credible. The agreement with observations is where we had a lot of discussions with Alberto. I'm not saying it agrees with observation. I'm saying that when we actually looked at daily observation data sets, we have a global data set and several regional data sets, and we looked at these indices, we found trends between the 70s and the 2010s, up to the middle, like 2005 or something, that were consistent with what the models were saying. This is all I said. More than this, I don't think I can say, because otherwise he will get very upset, because we discussed this, and Alberto thinks this may be what the trend we are seeing could be inside a natural fluctuation, at least for extreme or so on, but at least they're consistent. At least they're not the opposite, and I think that's good news.
Other questions? Please, don't hesitate. Yeah, please.
Yes, those were nice indices of stress, and I'm thinking about how the social political aspects are there between the precipitation and when you add population there. But have you thought about an index for food also?
Well, thanks very much for this question, because this is really the direction that we would like to go, and but of course we need help, because also the reviewers of this paper said, but these are sort of potential stress. You have to attach these real impacts, because you have an extreme event, you don't know what the impact is. I mean, you have to somehow measure the damage. But of course, this is very difficult to do. It's very difficult to do at the global scale. I think at the regional scale, for example, for Europe, this can be done by adding information about, for example, food production or actual damage, cost of damage. I think the insurance companies have this type of information. But the nice thing about this approach is that it's very simple to do. If you can attach some numbers to the damage or to the potential stress associated with these events, it can actually be done relatively simply. So I hope that if somebody working in impacts or in socioeconomic aspects of the global warming debate are interested in this, please give us a call, because this is the next step that we should go. And of course, we could also devise more complex climate indices, for example, adding sea level rise or things like that.
We may have time for one last question, if any. Okay, I assume that there are not any more questions.
Yes.
So with that, I'm closing the Alexander von Humboldt Medal Lecture for the year 2018. I would like to thank Filippo. The talk was exciting, and also the discussion. I think the point that the audience made are indeed very relevant, and point out also further and future avenues for research. I also would like to thank you very much for attending. Again, I'm very pleased to see a so large attendance. Indeed, the topic and the scientific challenges are very relevant. Thank you. I wish you a productive Thursday and Friday at EGU.